Hi, my name is Serena Sabori, and today I will be teaching you about implicit differentiation. We have learned so far how to take the derivative of a function when the function is expressed with one variable explicitly in terms of another variable. But what happens when we need to take the derivative of a function that is in a relationship of both x and y values? Take the equation of a circle, x squared plus y squared equals 16. It would be very difficult to set this in terms of x and differentiate from there. So in these cases, we use a process called implicit differentiation, which is the process of differentiating to x and solving the resulting equation for y prime, or dy dx. So we have our equation, x squared plus y squared equals 16, and we want to take it with respect to x. So that this becomes 2x. And now that we have the y term, because we want to find dy dx, or y prime, we have to multiply the term by dy dx, which is one of the basic rules of implicit differentiation. And the derivative of 16 is equal to 0. And from there, we want to separate dy dx from the rest of the equation. So we move all terms that do not include dy dx to the other side of the equation. So negative 2x would go here. And from there, we want to solve for dy dx. So we now simplify to negative x over y. So in some cases, we will be asked to find the second derivative of a function, or y double prime, using implicit differentiation. So in this case, we first need to find the first derivative and then differentiate that to find the second derivative. What we did with the previous problems is we're first going to differentiate both sides. We move our common terms to one side. And we solve for dy dx, which would be negative 8x cubed over 8y cubed, which is equivalent to negative x cubed over y cubed. And from there, we know that this equals to y prime, so we're going to differentiate this one more time to find y double prime. So at this point, we know we need to apply the quotient rule to this to differentiate it. We use low d high minus high d low. So it would be by dy dx. So from there, I'm going to clean it up a little bit first and then plug in dy dx. So I'm going to substitute my value of dy dx into the equation. As you can see, we can cancel out these y's with these y's. So from there, because I want to make the numerator more simplified, I can multiply the numerator and denominator by y over y. From here, we can actually factor out a negative 3x squared from the numerator. And if you recall, our beginning equation that we started off with was 2x to the fourth plus 2y to the fourth equals 64. And if we factor out a 2 from both sides, we're left with x to the fourth plus y to the fourth equals 32. So actually, we can plug this in. We can plug 32 in for the value of y to the fourth plus x to the fourth. And we are left with the final answer of negative 96 x squared over y to the seventh. The last major application of implicit differentiation is proving the derivatives of trig inverse functions. Let's say we are given sine inverse of x equals y, and we need to find the derivative of it. So using what we know about inverse functions, we know that this is equivalent to this. Sine y equals x. And from there, we can use implicit differentiation to find the derivative of sine inverse of x. So first we differentiate both sides. In order to express this ratio with x values, we can use a right triangle and set this angle equal to y. And because we know that x equals sine of y, and sine is opposite over hypotenuse, we know that the value of this side is x, and the value of the hypotenuse is 1, making sine of y equal to x over 1, which is x. And to find the last side, b, we can use Pythagorean theorem. Which we can plug in to this expression, which would equal 1 divided by cosine of y, which is 1 minus x, root of 1 minus x squared, and set it equal to the derivative of the inverse of sine x. So the derivatives of the 5 other inverse functions are as follows, and need to be committed to memory, but can all be proven using the previous method. We have the function y equals tan inverse of 2x squared. So using the derivative of tan inverse of x, which is 1 over x squared plus 1, we can find the derivative of this equation. So first, we need to differentiate both sides. So y prime equals, and we need to plug in 2x squared into the x value, and multiply that by the derivative of 2x squared, which will become 4x.
So
Y prime equals 4x over 4x to the 4th plus 1. Thank you for watching my video on implicit differentiation.